Hi everybody, welcome to part 2 of the summer assignment notes. We're going to start chapter 3. Chapter 3 is going to have 2 videos. Chapter 3 is all about measurements. So in the first video we're going to talk about scientific notation, metric conversions, and then in the second video we're going to talk about sig figs. So just like chapter 1, the packet will start with the poem and then the learning targets. Following that is going to be the guided notes that we're going to go over together with the videos. And then you're going to find 4 worksheets. Those are going to be part of your summer assignment, so you need to do those before the first day of school in August. Then you will find the sample problems. You don't have to worry about those. We're going to have a test sometime in August or September over chapter 3 when we get to it. Don't worry about it for now. And then you'll also find some labs that we're going to do at the start of school as well. So for now, all you need to worry about is take the notes over the first few pages and then do worksheets 1 through 4. So we're going to start the notes for chapter 3 with scientific notation. Since we said that chemistry is the study of matter and the changes that matter undergoes, we need to be able to make observations for matter. And observations a lot of times are descriptive, but also a lot of times are quantitative where you put a number. So in science, like in chemistry, we deal a lot of times with molecules or atoms that are really, really, really small. In other sciences, if you talk about planets, for example, then you're talking about something that's really, really, really big. And so when we write really, really big or really, really small numbers, it's hard for our brain to process them. And so a way to show those numbers in a simpler form for us to be able to look at the number and be able to tell how big or how small it is using scientific notation. And I know you are all experts in scientific notation, so we're going to review them very quickly. So in scientific notation, you have a number. This number has to be between 1 and less than 10. So if it says 0.032 times 10 to the third, for example, that is not scientific notation. Or if it says 32 times 10 to the third, that is not scientific notation. So this number needs to be between 1 and less than 10. Then you'll see times 10 to some power. If that power is positive, that tells you that that's a pretty big number. That tells you that it's, greater than 1. If this number is negative, then that tells you it's a really small number. So that means this number is smaller than 1. So to go from scientific notation to longhand, what you do is you use the number that's the power of 10. That's how many times you move your decimal point, or how many places you move your decimal point. For example, if you have 3.2 times 10 to the third, that means that I need to move my decimal 3 places. Since it's a positive exponent, 10 to the third, positive third, that means I move it to the right. Or if you think about it, positive means it's a big number, so I'm going to move it this way. So there's 1 time, 2 times, 3 times, and then fill in zeros for your blanks there. So the number is 3200. So it's a pretty big number. It's 3,200. Let's look at the next one. So 5.5 times 10 to the negative fourth. So that tells me that I'm going to move my decimal point 4 places, but because that's negative 4, I'm going to move it to the left. So you can think negative is left, positive is right, or you can think positive big number, negative small number. So I need to make it smaller, so I'm going to go 1, 2, 3, 4, and I put my decimal point there. So then I fill in zeros. So it's 0.00055. Pretty small number. Okay, if I want to go the other way around, so I want to go from longhand to shorthand, or sorry, longhand to scientific notation, what you do is you keep moving your decimal place until you get a number that's between 1 and 10, like we said. So I'm just going to make it bigger so you can see it a little bit better. So the first number doesn't have a decimal point in it. So if there were a decimal point, it would be right here. So then you keep moving it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is where I want to keep my decimal because 7.4 would be a number between 1 and less than 10. So I would write 7.409 and then times 10 to the power, and I forgot how many there were, so I'm going to count it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's 14. And in this case, it's a positive 14 because it's a really big number. Next, 0.084. So here's my decimal point. I'm given a decimal point in this case, so I'm going to move it until I hit a number between 1 and less than 10. So there's 1, 2, and this is where I stop because 8.4 would be a number between 1 and less than 10. So I moved it only 2 places, but it's a -2 because I moved it to the right or because it's a number smaller than 1, whichever way you want to think about it. So scientific notation is pretty easy. Just review it. Make sure that you know how to do it. Our next topic is SI units. So SI units are units that are agreed upon internationally to be used in science. And so in the US, we typically use the English system. So we use gallons, we use inches. In other countries, they don't usually use that. They use the metric system. And so the SI units stand for Système International. That's why it's SI as opposed to IS. But it's an international system of units that can be used throughout science all over the world so that when people publish papers in different countries, other scientists can read them and understand what they're talking about. So there are basic SI units for length, mass, time, electric current, temperature, amount, and intensity. So let's go over those real quick. You do need to know what the SI unit for each of these is. And so for length, the SI unit is meter, and the symbol for meter is lowercase m. For mass, the SI unit is kilograms, that's kg. So let me talk about this for a second. So meter is about the length of a yard. It's not exact, but it's close to a yard. So it's about 3 feet, just so that you're familiar. So if you open up your arms, that's about a yard or about a meter. For mass, it's kilogram. A kilogram is a little bit over 2 pounds. It's like 2.2 pounds, something like that. So think of, go to the store over the summer and find something that's about 2 pounds, like a box of pasta or a packet of meat or something like that. Hold it in your hand. Think about how heavy that is. That would be, about 2 pounds would be a kilogram. Time, thank goodness, that's common between all countries. So we use seconds as the SI unit. So you know about how long a second is. Electric current is something that we're not really going to use very much. But it's an ampere. We're not even going to talk about that until AP Chemistry. So if you're not going to take AP Chem or Chemistry in college or Physics, then you're not going to really need to worry about what an ampere is. But it's the SI unit for electric current. Temperature is something that we use a lot. The SI unit for it is Kelvin. Now, most people, whether they're in the US or in any other country, are not as familiar with Kelvin as they are with the other units for temperature. So here we're familiar with Fahrenheit. In most countries we're familiar with Celsius. So we're going to be using Celsius and Kelvin in science, in chemistry class. So just so you have a frame of reference, I think most of you know that the freezing point of water is 0 Celsius, which is 32 Fahrenheit. The boiling point of water is 100 Celsius, which is 212 Fahrenheit. Comfortable room temperature, which is about 75 Fahrenheit or so, that's 25 Celsius. So, you know, just be familiar with Celsius. Kelvin is same as Celsius, but you add 273 to it. And we're going to talk about how to convert in a little bit. Next is amount of substance. That's mole. And, you know, chemists are very lazy. And so to abbreviate mole, they went with MOL. So they don't have to write the E. This we're going to be using a lot in chemistry, but probably towards the end of first semester. Luminous intensity is a candela. And again, this is not one that you will really need to worry about. Even in AP chemistry or chemistry in college, you're not going to talk about candela very much. This is more of a physics unit when they talk about light. But just be familiar with all of them. Now, any other unit that you can think of is a derived unit. That means it's not a basic unit. So it's derived from several of these units. So here are some examples. For example, let's say you want to know area. And so if you're talking about a rectangle or a square or something like that, what you do is you do length times width. Where's my pointer? Here it is. So length times width. So this is distance, and this is also distance, so meter times meter, so that would be meter squared. So the unit for area, the basic unit for area is meter squared, which is a derived unit. It's derived from multiplying two length units. Similarly, volume would be length times width times height. So meter times meter times meter, which would be meter cubed, or a cubic meter. And so again, this is a derived unit. Density is mass over volume. And so it looks like it's missing from the table there. So mass, we use kilogram divided by volume. We just said that volume would be meter cubed. So kilogram per meter cubed would be the SI units. Again, there's a lot of other units that we can use for density or for volume or for area or for any of these, but these are the SI units. Next is molar mass. That's something that we're going to talk about later when we learn about what a mole is. But it's mass divided by amount, so kilogram divided by moles. Energy, the unit for it is a joule, which is derived from these. So energy is measured in joules. Now, capital J is an abbreviation for a kilogram meter squared per second squared. That's what a joule is. Let me write that down. Not that you need to memorize it or anything, but 1 joule is 1 kilogram meter squared over second squared. So it's mass times length squared over time squared. And so that turns into a joule. Similarly, pressure is force per area, which is a Pascal, which again is derived from all these units. So any unit that you see that's different from these, they are derived from those SI units. All right, so these SI units are great, but like we said, in science, sometimes we are talking about very, very small things or very, very large things, and we can use scientific notation. But sometimes to just make it simpler, we use prefixes to make our unit either really small or really big to describe, you know, something that is, you know, really, really submicroscopic or huge, so that our numbers that we use are simple numbers or easy numbers for our brain to process. So if you look at this chart of metric prefixes, and I know you're all familiar with metric prefixes because you've used them before, the basic or the base unit, which is different from the SI unit, the base unit, that means it does not have a prefix in front of it. It's just the unit without a prefix. Those would be grams, meters, or liters. Okay? You can add a prefix in front of any of these units in order to make it, like we said, either really big or really small. So let's go through some of these prefixes, for example. So deca, that means that it's that unit times 10, or 10 to the first power. So in this table right here, this is times 10 to whatever power. So the base unit would be times 10 to the 0 power, which is just 1. So it's times itself. Deca means times 10 to the first, so basically times 10. So for example, a decameter would be 10 meters. A decagram would be 10 grams, and so on. A kilo is that unit times 10 to the positive 3, so like 1,000. 10 to the third is 1,000. And so a kilometer is 1,000 meters. A kilogram is 1,000 grams. A kiloliter is 1,000 liters. Mega is 10 to the 6, so that's a million. So a decameter is 1,000,000 meters. And then giga is 10 to the 9th, and so a billion. So gigameter would be 1,000,000,000 meters. So deca gets either capital D or DA. I've seen it both ways. Kilo is K, mega is capital M, and giga is capital G. How about 10 to the 12th? Anybody know what that is? If you think computers, tera. So like a terabyte, that's 10 to the 12th bytes. All right, going the other way, so going the smaller way, we have deci. So deci is 10 to the negative first, so a tenth. So a decimeter is a tenth of a meter. Centi is negative 2, so 100th. So a centimeter is 100th of a meter. Milli means negative 3, 10 to the negative third. So that's 1,000th. So a thousandth of a milliliter, or sorry, 1,000th of a liter is a milliliter. Micro, that didn't show up. Micro gets the symbol mu. It's a Greek letter. It's pronounced as M, but it's written as a fancy U, kind of like that. Anyway, micro is 10 to the negative 6. So a millionth of a meter is a micrometer. Nano is negative 9. So a billionth of a meter is a nanometer. It's really, really small. A lot of atomic radii. So the radius of an atom is usually measured in nanometers or picometers. Pico is negative 12. Okay, so how do we use these prefixes? If you want to relate one unit to another with prefixes, what you do is you always put the big number next to the small unit and the small number next to the big unit. What that means is, let's say we're talking about money. So let's say we're talking about $1 versus a cent. So which of those is the big unit, which is the small unit? So dollar versus cent, $1 is the bigger unit, the cent is the smaller unit. So I'm going to write cent here, and I'm going to write dollar here. So you know the relationship between them is 1 versus 100. And so if you're not sure, it always works out if the big number is with the small unit and the small number is with the big unit. So that means between 100 and 1, 100 is the big number, so you put that next to the small unit. So 100 cents are equal to the small number next to the big unit. 1 is the small number, dollar is the big unit. So 100 cents are equal to $1. It's never the other way around. So if you're ever doing a conversion factor or you're converting between one and the other, if you ever put the big number with the big unit or the small number with a small unit, you know that you're doing it wrong. It always has to be big, small, or small, big. Okay, so how do we use that? Let's try. There are different ways to do metric conversions, and I know you've done it before. So for some of you, you know how to do it. You're pretty sure that you're getting it right all the time. If you are 100% sure, then just do it whichever way you want to. I'm okay with whatever way you want to do it as long as you're getting the correct answer and you're also showing me some kind of work. So just don't do it in your head. You got to show me some work. If you're not sure or you don't know how to do it, or you do it, sometimes you get the right answer, sometimes you don't, or you're just not 100% sure, then I'll show you a way and always use that way. Again, if you're not sure, but if you are and you have your own way to do it, then go for it. So what I do is a little bit longer, but later on when we do more complicated chemistry, all our calculations are going to be that way. So if you do it the way that I show you now, it's going to help you in the future when we do the harder problems. And what I do is I use the dimensional analysis. Some people call it the train tracks. And so what you do is, let's say you want to do convert 22.6 millimeters into meters. So what you do is you write down what you have. So you write 22.6 millimeters. That's what we have. Okay. Then you do a conversion factor. So so you multiply. I'm going to write, this is a multiplication sign, and then a conversion factor is a fraction. So something divided by something, and those two things are equivalent. They are equal to each other. And so when you put something divided by something and both of those things are equal to each other, that equals 1. So it's as if we're multiplying it by 1, which is basically getting the same answer. So that's why it's okay to do a conversion factor. So anyway, again, the conversion factor is a ratio or a fraction where the top and the bottom are equal to each other. So you start with the units. You don't put numbers yet. On the bottom of the conversion factor, you always want to put the units that you are given. So here I'm given millimeters, so I'm going to put millimeters on the bottom. The reason for that is because when you multiply this through, if you have something on top and something on the bottom that are the same, they can cancel out. So if those units cancel out, then you get rid of the millimeters because you don't want it anymore. Okay, so whatever you're given as units, you put them on the bottom so they cancel. On top, you put the units you are looking for. So in this case, I'm looking for meters. So I'm going to put meters on top. Then you look at what numbers to put. So we want to compare between meters and millimeters. So you go back to the table of the metric prefixes that we have. And what I always do, because sometimes it's times 10 to the positive 2 or 10 to the negative 2, and people get confused whether you put a positive or a negative. So what I always do is I find the unit that's bigger and I put a 1 next to it. So between meter and millimeter, which is the bigger unit? Is a meter bigger or is a millimeter bigger? A meter is bigger. So next to the bigger unit, always put a 1. Next to the small unit, you're going to put 10 to some positive power. We don't know what that power is yet, but it's always going to be positive. To figure out what that power is, you look at your table and you compare your prefixes. So I'm going to go back to look at the table real quick. Okay, so let's look at the table. So meter doesn't have a prefix, so that means it's a base. It's right there. Milli is right here, so let me box those. So there's the base, that's my meter, and there's my milli. The positive difference between them is what I put there. So this is -3 and this is 0. So the positive difference between them is 3. So this is 10 to the third. Okay? So now when I do my math, millimeters cancel with millimeters, and I end up with meters. And so it's 22. Anything on top you multiply, anything on the bottom you divide. So it's 22.6 times 1 divided by 10 to the third, or 1,000. So that means that it's 22.6 basically divided by 1,000, which is 0.0226 meters. So I'm going to write that down, 0.0226 meters. Okay, let's try another one. So the next one that I'll try is 0.61 kilograms. I want to convert that to centigrams. So first step I do is I write down what I have. So 0.61 kilograms. Then I start a conversion factor. On the bottom, I want the same units that I have here so they can cancel. So I'm going to put kilograms. On top, I want the units that I'm looking for, which are centigrams. So I'm going to put centigrams. Then I figure out which unit is larger. So is a centigram bigger or is a kilogram bigger? A kilogram is much bigger. So my bigger unit gets a 1. My smaller unit gets a 10 to some positive power. So to figure out that power, then we go to our table. So in our table, we have centi and we have kilo. So I'm going to box these in blue. So centi's right here. Then kilo is right here. Okay, so we're looking at the blue boxes there. Okay, so -2 and +3. What is the absolute difference between -2 and +3? That would be 5. The difference between them is 5. So then I'm going to go back to my calculation here, and that gets 10 to the +5. So then when I multiply through, my kilograms and kilograms cancel. I end up with centigrams as my unit. And it's 0.61 times 10 to the 5th divided by 1. So basically 0.61 times 10 to the 5th. So that means I move the decimal place 5, or decimal point 5 places. So let's see, that would be 61000 centigrams. That would be my answer. All right, last one here. 78.5 milliliters. I want to convert that to liters. So I'm going to write down what I have. So 78.5 milliliters. Conversion factor. On the bottom, I'm going to put milliliters so they cancel. On top, I'm going to put liters because that's what I want. I compare liters with milliliters. Which one's the bigger unit? My bigger unit is liters, so I'm going to put a 1 next to that. Then next to milliliters, I'm going to put 10 to some positive power. So let me go back up here to see what my positive power is. So milli is right here. It was already in black. Let me do it in red this time. So milli. And then liter is the base. So between milli and base, that's 0. That's -3. So the difference between them is 3. So I'm going to put a 3 right here. So my milliliters cancel. So it's 78.5 times 1 divided by 10 to the third. So basically 78.5 divided by 10 to the third, which is you move the decimal place, or decimal point 3 places to the left, so 0.0785 liters. All right, let's look at the next set. These are a little bit harder, I think. I want to go from centimeters squared to millimeters squared. 12.0 centimeters squared to how many millimeters squared? Now, this is not length. What would this measure? Meter squared or centimeter squared or millimeter squared? That would be area. Length times length. That would be area. So I know the relationship between a centimeter and a millimeter, but I don't know what the relationship is between centimeter squared and millimeter squared. So how would you do that? So you start the same way. You write down what you have. So I have 12.0 centimeters squared. You start your conversion factor. On the bottom, you want to put the same units that you have. Now, for now, I'm going to ignore the squared. I'll come back to it. So for now, I'm just going to write centimeter here without the squared. And on top, I'm going to put the unit I'm looking for. So I'm looking for millimeters squared. So for now, I'm going to ignore the squared. I'm just going to put millimeters. The reason why I didn't put the squared is because, like I said, I don't know the relationship between a centimeter squared and a millimeter squared. I know the relationship between a centimeter and a millimeter. So let's find the relationship between these first. So a centi or a millimeter is bigger. A centi is bigger. So that gets the 1. And then the milli gets 10 to some power. So let's figure it out. Let's see. So milli and centi are right here. So centi is -2, milli is -3, so the difference between them is just 1. So I'll go back to my problem. So this is 10 to the first, or just 10. You don't need to put the 1 there. All right, now, again, this is the relationship between a centimeter and a millimeter, not the squares. So then what you do is you square the whole thing. You square this whole thing. When you have parentheses and then a squared, that means that squared distributes to everything. So that goes to the 10, it goes to the millimeter, it goes to the 1, and it goes to the centimeter. So let me rewrite this so it looks a little bit better. So I have 12.0 centimeters squared times, okay, 10 squared, 10 to the first squared would be 10 squared, or 100. Then we have millimeters squared. 1 squared is just 1, and then centimeters squared. So that way, I figured out the relationship between a centimeter squared and a millimeter squared. Now, I can multiply this through, so centimeter squared and centimeter squared cancel. My units are millimeter squared that are left, and then it's 12.0 right here times 10 to the second, so times 100 basically, so 1200. So the answer is 1200 millimeters squared. Okay, let's try another one. Okay, so 2.41 meter cubed is how many decimeters cubed? So let me do that in red. So you write down what you have first, so 24.1 meters cubed. You start a decimal or a conversion factor. On the bottom you want the same units, but for now I'm going to ignore the cubed. On top you want decimeter cubed, but again for now I'm going to ignore the cubed because I don't know what the relationship is between a meter cubed and a decimeter cubed. I know the relationship between a decimeter and a meter though. So meter versus a decimeter, meter is bigger, so that gets the 1. Decimeter is smaller, so that gets 10 to some power. To figure out that power, go back to your table. We have base unit, which is meter, and then we have a deci. So 0 and -1, so the difference between them is just 1. So back to my problem here, that would just be 1 right here, or you can leave it blank if you want. It's up to you. You can put a 1 or you can just leave it as just 10 to no power. All right, now that's the relationship between a decimeter and a meter. But I want meter cubed to decimeter cubed. So then I cube that whole thing. So that cube distributes to everything in my parentheses. So let me rewrite it, 24.1 meters cubed. Okay, 10 to the first cubed is basically 10 to the third. That would be decimeter cubed. 1 cubed is 1, and then meter cubed. So my meter cubed and meter cubed cancel. I end up with decimeter cubed. And so it's 24.1 times 1,000. So 24,100. 24,100 decimeter cubed. So these are a little bit more tricky, so make sure that you know how to do these. Okay, now with the basic units, the SI units that we had talked about, we talked about length in meters. We never really talked about volume. Well, we said that volume is a derived unit. So if you want volume, it's length times width times height, which is meters times meters times meters, which is meter cubed. But then when we talked about the basic units, we just jumped to a liter. So you want to know what is the relationship between a meter cubed or a length cubed versus a liter. So I think most of you know that a milliliter is equivalent to a centimeter cubed. So what does that mean? Think of a cube. That's 1 centimeter by 1 centimeter by 1 centimeter. So if I take a cube, a centimeter is like half an inch or so. So if I take, and I can't draw very well, but let's say that's a cube here. And the dimensions of this cube is 1 centimeter by 1 centimeter by 1 centimeter. So that the volume of this cube is 1 centimeter cubed. Then that volume is equivalent to 1 milliliter. Okay? Now think of a bigger cube, a decimeter cubed. A decimeter is 10 centimeters. So think, I don't have a very big screen here, but so let's say that's 10. It's a little bit smaller, but let's say that's 10 centimeters. So obviously that's not a cube even, but let's say that this is 10 centimeters by 10 centimeters by 10 centimeters. So that would be 1 decimeter cubed, because a decimeter is 10 centimeters or a tenth of a meter. That is equivalent to 1 liter. And when we go back to school in August, I'm going to show you, show you a decimeter cube, and then we'll pour a liter of water in it and see if it fits. These are relationships that you need to know or memorize. So you need to know that a milliliter is the same thing as centimeter cubed. A liter is the same thing as a decimeter cubed. So let's try some conversions with these. So let's say I have 21 milliliters. I want to know how many centimeters cubed that is. It should be the same thing because a milliliter is centimeter cubed. If you wanted to show work for that, which, you probably don't, but if you really wanted to, you'd say milliliter on the bottom so it cancels, centimeter cubed on top, because that's what you want, and based on this relationship, we know that 1 centimeter cubed is 1 milliliter, so that cancels, you get 21. Similarly, if you were doing 6.3 decimeter cubed in a liter, it's the same thing, 6.3 liters. Again, if you wanted to show work for that, you'd say, okay, well, the conversion factor on the bottom, you'd put a decimeter cubed. On top, you'd put a liter. And based on this relationship, this relationship here, 1 liter is 1 decimeter cubed. So 1 and 1, that cancels. You end up with 6.3 liters. All right, so these are simple. What about the next two? Those are a little bit harder. So let's say I have 3.7 liters, and I want to know how many centimeters cubed that is. So I'm going to start with what I have, 3.7 liters. On the bottom, I'm going to put liters. But the problem is, I normally would put centimeters or centimeters cubed or something like that here. I have no link between centimeter cubed and liters, or even centimeters and liters. No link whatsoever. I can't link between them, so I can't put numbers here. That means this is a two-step problem. So you have two choices. You know the relationship between a liter and decimeter cubed, so you can convert from liters to decimeter cubed, and then you can link between decimeters cubed and centimeters cubed like we did earlier. Or another way you could do it is you could convert from the liters to milliliters using our conversion factors, our metric conversions, and then you can convert between a milliliter and a centimeter cubed. Both ways will work just as well. I think it's easier to go from liter to milliliter so you don't have to mess with the cubed, but both of them will work. So let me show you both ways, and you pick which one you want to do. So the first way I'm going to do it is I'm going to go from liters to milliliters. And so based on the metric conversions that we just did, a liter is a bigger unit than a milliliter. So this gets a 1. This one gets 10 to some power. And if you compare them, liter is the base, milli is -3, so the difference between them would be 3. And then you do another conversion factor. So now liters and liters cancel. You end up with milliliters. So now you put the milliliters on the bottom. So these two cancel. And then you put centimeter cubed on top. And you know the relationship between a centimeter cubed and milliliter based on this. It's a 1 to 1. So now your milliliters also cancel, and you end up with centimeters cubed. So it ends up being 3.7 times 10 to the third times 1 divided by 1 divided by 1. So you can ignore those ones. So 3.7 times 10 to the third, so 3,700. Okay, let's do it the other way just for fun. So if I were to do it the other way, I would say 3.7 liters. On the bottom I put liters, on top I put decimeters cubed. It's a 1 to 1 based on this relationship. And then I'm going to say decimeters on the bottom, centimeters on top. 10 centimeters are 1 decimeter. That's from my metric conversions earlier, but then I cube it, so it's really 10 cubed, 10 centimeters cubed over 1 decimeter cubed. And so it'll end up giving you the same exact answer. Okay, let's try this one here. I'm running out of space, so I'm going to put it up here. So I want 4.89 decimeters cubed going to milliliters. So I'm going to write down what I have, 4.89 decimeters cubed. Start a conversion factor. On the bottom you want to put decimeters cubed. On top you'd like to put milliliters, but there's no link between milliliters and decimeter cubed, so that tells you that there are two steps. So I'll show you both ways to do it. There's two different ways. You could go from decimeter cubed to milliliters. I'm sorry, decimeter cubed to liters. And then you can link between liter and a milliliter. I think that's the easier way. So I'll do that first. So liter here, 1 to 1. Now my decimeters cancel that way, and so I end up with liters. And so I'm going to put liters on the bottom so it cancels. Milliliters on top. And a liter is bigger. This is 10 to the third. That's a 3 there. And so my liters cancel. So 4.89 times 1 times 10 to the third divided by 1 divided by 1. So basically 4.89 times 10 to the third. So 4890 milliliters. Let me do it the other way just for fun. So 4.89 decimeters cubed. So another way to do it would be to link between decimeter cubed and a centimeter cubed and then go to milliliter. So decimeter on the bottom, centimeter on top. 1 decimeter is 10 to the first centimeters, but then you cube everything. So this would be 10 cubed, centimeter cubed, 1 cubed is 1, decimeter cubed. That way your decimeter cubed cancel. Then your second step would be to put centimeter cubed on here, milliliters here, and according to this, 1 and 1, so your centimeter cubed cancel as well. So 4.89 times 10 to the third times 1 divided by 1 divided by 1. So 4890 milliliters. So you get the same answer no matter what. So you can pick one of those two ways. This is easier. It's always easier to convert milliliter to liter than it is to do, meter cubed or centimeter cubed or decimeter cubed or something like that. Anything cubed is harder just because you have to do that second step where you cube it. All right. Next part is temperature, conversions in temperature. These are a lot easier than the metric conversions, I think. So in the United States, we usually use Fahrenheit like we talked about, but in science, we usually use either Celsius or Kelvin. Now, to come up with a Celsius scale, what they did was they got a tube, filled it with mercury, and they put it in boiling water. They marked where the mercury was. Then they put in ice water. They marked where the mercury was. And they said between those two, that's going to be 100 points. So they said where it was at its lowest point, where it was in cold water, ice water, it was 0. That's 0 Celsius. In boiling water, that's going to be 100 Celsius. And then anywhere between, you can divide them equally. So like I said, about room temperature is 25 Celsius. The problem with that is that gave us negative values because it can get colder than ice. Or ice can get below 0, below its freezing point. And so there were negative numbers, which in some calculations didn't make sense that we would get negative numbers. And so they wanted a scale where everything was positive. All temperatures would be positive. And so they calculated what absolute 0 should be. Absolute 0 meaning that's the coldest temperature it could ever go to. That's where molecules just stop moving whatsoever. That's going to be the coldest temperature could ever be. That's going to be our 0 for the new scale, which they called Kelvin. And so absolute 0 is 0 Kelvin, which when they calculated turned out to be negative 273 Celsius. Now it's really negative 273.15 something, 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 but for now, just go with negative 273. So the Kelvin temperature is always higher than the Celsius temperature because remember, Kelvin can never be negative. So it's always going to be the higher value. So if you want to calculate the Kelvin temperature, you take this Celsius and you add 273 to it. If you want the Celsius temperature, it's going to be lower, so you take the Kelvin temperature and subtract 273 from it. Okay. Notice that when we write a temperature, if it's Fahrenheit, we write degree Fahrenheit, or if it's Celsius, we write degree Celsius. With Kelvin, it's just kelvins. There's no degree. So let's try one. 25 Celsius going to Kelvin, so I know that's going to be a bigger temperature, so I would say 25 plus 273, so that's 298 Kelvin. So 298 Kelvin. Oops. Just 298. 312 Kelvin, we want to go to Celsius. So you're going to say 312 minus 273. So that's 39 degrees. So the answer is 30. Our next topic is density. I know, again, this is something that you've talked about before. So all this summer assignment really is just review for stuff that you have taken in your previous science classes. So density is mass over volume. So let's review what mass and volume and all that is. So we'll start with mass. Mass is a measure of the amount of matter in an object. So it's essentially how much stuff is inside the object. So that should never change. Weight, however, is the force that mass exerts as a result of gravity. And so when gravity changes, the weight will change, but the mass will remain the same. For example, let's say I'm 120 pounds on Earth. If I go to the moon, gravity changes. So I'm no longer 120 pounds, but I am the same number of kilograms. So I'm the same mass, whether I'm on Earth or the moon, but I have a different weight, whether I'm on Earth or on the moon. Volume is the amount of space that the object takes up. So that will always be the same for solids or liquids. It does change with temperature slightly, but if we're talking about the same temperature, it should remain constant. So then density is the amount of matter, so mass, per amount of space, so per volume. So you take the mass divided by the volume. As long as you're keeping it at the same temperature, density should not change. So whether you have a cup of water or a bucket of water, the density of water is 1 gram per milliliter at room temperature. So that never changes. It's just 1 gram per milliliter, whether you have a lot of it or just a little bit of it. To help you remember that density is mass over volume, you can think of density as a heart with a line through it. So there's the M and then there's the V, if that helps. So let's try a problem. It says, what is the volume of a substance with a mass of 75.8 grams and a density of 7.87 grams per centimeter cubed? So I'm going to write my density equation. So density is equal to mass over volume. I'm given the density, it's 7.87 grams per centimeter cubed. I'm given the mass, it's 75.8 grams. I don't know what the volume is, so that's what I'm solving for. You can write a V there, or you can write an X if that helps. So then you would do 75.8 grams divided by 7.87 grams. You can punch that into your calculator. And so you would get that the volume is 9.63, and the units for that, your grams and grams cancel, so that's in centimeters cubed. And so that was your answer. All right, the next part is going to be video number 3. So we are going to talk about sig figs next, and that will be the last part of the notes for the summer assignment. So watch the 3rd video and then make sure that you do your worksheets. Have a great rest of your summer.